Okay, I'm back. I have my smoothie and I'm ready to resume coding on this Carleson project lemma. I did like a little bit. I thought over what I was thinking through yesterday, and I feel like there's maybe a simpler solution, or a solution that doesn't rely on like massively like playing around so much with all the exponents and logs and such. And I was also, so I guess one thing that I was doing is I was trying to like prove this lemma, which I needed. So it turns out I think that this is the right 0 less than b rather than b not equal to 0 is the correct hypothesis. And so I'm basically trying to prove it. Someone mentioned, let me see if I can go to the lean zulip. Lean zulip. I'm logged in, wonderful. And it would have been in, is there code for x? Convex pow, yes, right. Should be obtainable by scaling strict convex on exp. Yes, I mean, I agree. So that's what I'm trying to do here. So I'm trying to prove this, and the first step is to say that b to the power x is equal to e to the log b times x, which I've proven here and on this, so that's all good. And apply is not getting me anywhere now. So what I need to do now is, what do I need to do now? What I need to do now is I need to find the fact, okay, so I have a linear rescaling of a function, and exp is a convex function, and I have strict convex on exp. So I need to figure out how I like express the fact that if I have k times x, then exp is like, it's a convex function because it's a convex function applied to a linear function. Where is that? Moogle, maybe Moogle will tell me. Composition of convex function with linear function is convex. Convex with 2 x's. Convex linear image. Right. Okay, so important to remember from yesterday that convex without the on afterward is a statement about sets. So this is a statement about sets, and this is not exactly what we want. F is a linear map, then it's convex on a linear map. Well, yes, a linear map is convex, yes, but that's not quite what we want. What we want is that comp linear map. This is looking good. Convex on comp linear map. Convex on comp linear map. This is looking correct. If G is convex on S, right? Yeah, forget about the like sets for now. So is F of G. Sorry, let me think through here. The first thing we're doing is multiplying. So G, no, this is not quite what we want, right? So in this case, G is the multiply by log b function, and f is the exponential function, which is not linear. So what we want is that the other way of composing them is convex. Is that this one perhaps? No. Concave on comp linear map. It's just the wrong order, right? Is this really not what we, let me think through this again. Convex on. I feel like there should be a tactic. Just let me go over. This seems like the sort of thing where they would have a tactic. Like they have a differentiability tactic, they have a positivity tactic, they should have a convexity tactic. Math Live for tactics. What is all tactics? Yeah, I'm not actually seeing it. Linear map, concave on. This is concave on, so we're back at concave. What is the, what was the thing that was almost right? Convex on comp linear map. So I would assume that it would be convex on linear map comp. Here F is a linear map E to F, right? Is the documentation for this right? let me read this. For a linear f. But that is clearly not what is said here. What is said here is that G is the linear map. Here, let me like try and like increase the size. Let me go to the docs. Oh my god, I want to go to docs. MathLab docs. Yes. This place. For a linear f. No. That's not what you're saying here. This is G. G is the linear map. Okay. This is poor documentation. I should make a note to myself. Yeah, the wonderful thing about recording yourself doing things is that you can recall things later. So I should go and fix this. But I think it's good for my current purposes because it means that this is the right lemma for me to use. So like returning over here, I want to like, let me try and apply this. Well, actually what I want is strict convex on comp linear map. Let me see if that, yeah, annoying that doesn't exist. Maybe we try and prove this for convex on, because that was all that we really need. Failed to unify unknown constant, right? Okay, so this is all sorry. I wonder if like the right thing to do is to like, so there should be like some sort of 2MATLAB folder here, and probably all of this should go in the 2MATLAB folder. Yeah, and then I can just leave out a sorry lemma in the 2MATLAB folder. Okay, I don't think I need this anymore, right? Okay, I'm getting an error. I'm getting an error because it's not of the form that is desired. Really? Okay. Yes. A simpler way of saying it would be right. Yeah, so I can so now this is taking the form of, I'm like writing this in a more point-free style. Ext simp, and now that's fine. Probably will comply. Okay, so rewrite this, and so now it's in the form of this composition. Apply, fail to unify, convex on. Okay, so what I need to do is like convert or whatever. Okay, let me try and be more explicit. Comp linear map. The so HF is convex on, yeah, so clearly HF is convex on whatever. So this is the convex on exp, right? So convex on underscore exp. Let me just like open this in a new tab so I can confirm that it's the right, yeah, convex on exp. Oh man, and I've lost my place over here. Convex on exp, convex on R univ, whatever, for all G. And then, okay, and now we have to specify G. We have to specify G as a linear map from the reals to the reals that multiplies things by B. Yes. I mean, the question, I guess, is like, how do I make this a linear map? How do I construct a linear map from is linear? F, right, a linear map is just a, how do I like create a linear map? Okay, the AI just produced this random thing, but I don't think that this is correct. Real linear map. Yeah, that like should be something like linear map mol. Linear map mol. Not mol. is a bilinear map. Multiplication is a bilinear map, yes, but it's also just a linear map. A bilinear map is defined as like a linear map of a linear map. Yeah, okay. Cool. So I think, yeah. So I think what I want is linear map mul of simply log b. Real.log b. Okay, that seems to be good. No, still complaining. Linear map.mul real.log b. Argument real.log b has type real, yes, but is expected to have some other type. Why do you have... Oh, I actually have to specify R and A. Okay. Yes, so clearly I am talking about the function which multiplies two real numbers together. So R is, I think these are both just R, right? R. Okay. No goals. Okay, wonderful. It just closed everything. Yeah, it's just done. Wonderful. Okay, cool. So that's good. Okay, so let me see if I can try and move this to a like a 2MATLAB. Let me save. So first of all, is the theorem name correct? Returning to like convex on exp. Convex on exp. Yes, collection of convex functions. So like presumably there should be like a 2MATLAB analysis convex specific functions basic, and I can put it there perhaps. My God, I'm getting a smoothie all over myself. Yes. So I should simply try and move this. Let me investigate. 2MATLAB. Yes, this is where it should go. And so 2MATLAB, I think the point is I just want to like completely replicate the directory structure. So why don't I do like make a new folder, 2MATLAB analysis convex / specific functions / basic lean. Oops, sorry, this was not right. I need to make a new file. .lean. Okay. I'm dumb here. I need to delete this. Delete. To trash. And then in special functions, I need to make a new thing called basic.lean. Cool. And what this should import is import mathLab.analysis. Yeah, that's good. And I'm hoping that I can, sorry, where am I? Is this where I was? Yes, okay. Okay, first of all, this is some old thing that was not needed. And I think I determined that this was not needed either. And so I'm simply saying that I can copy these away into this basic.lean folder. Unknown identifier comp apply. Well, let's look for where comp apply might be. Comp apply. Unknown identifier comp apply. Sorry, undo. Comp apply. Init core. That's annoying. Why is it not finding the comp apply in the init core? Unknown identifier comp apply. How is that possible? Declaration is sorry. That seems fine. Unknown identifier comp apply. What? How can you say that there you don't know the identifier comp apply? It's in is defined it's in init.core. So how can you say that? Function.comp apply is obviously. Is it that? Ah, yes. Open all of these namespaces. Except for this one. Okay, cool. Now it's pleased. And now I'm going to do import Carleson .toMathLab. And now we can restart. Is it going to need to like import a bunch of things? I hope not. Oh no. Have I screwed myself? Imports are out of date. It must be restarted. Do I restart file here? Okay, now it's saying already declared. Yes, that's very good. And like, if I don't want it to complain about like the sorry here, I can just, in theory, like comment this out. To do, not needed, but good for completeness. So that's fine. Save, restart the file. Okay, so we're back here. Yes, back here at this unsolved goals. So now let's like consider what we're doing. We're doing the real geometric series estimate. As we did last time, we figured out we don't need to like go into the non-negative reals. So we're just doing something about some real numbers here. We have this, sorry, which is why is this easy to prove? I forget. Oh no, the problem is that, sorry, what is going on? Convex on our pad left. In fact, it should be like a dot, right? No, it's just an underscore apparently, whatever. Okay, so that's cool. And this is just some brute fact about numbers. And we were here, right? We were trying to figure out like a plan. So I think, okay, what I was thinking of is maybe I can just return to the first plan. So the first plan was something like this. Let me like, I have like many plans upon plans. So let me like return here and do something like this, right? So what I was saying is I can do x minus 4, here, like here was my basic thinking. Like, let's say, let's forget about the restriction that x is only greater than 4, and let's just prove this fact for sufficiently large x. And then once we've proven it for sufficiently large x, we can come back and prove it for the smaller x by sort of like careful analysis of like how big each of the individual things is. So we have this equals 2x. We're trying to prove that 2x is greater than 2 to the power x is greater than 2 times x for sufficiently large x. So the first thing we're going to do is minus 100 plus 100. X minus 100 floor plus 100. 2 to the power 100 is a massive number. This is 100, right? This is 100. We can just delete this line actually. And like here, let us apply the lemma that says, the lemma that we have in our sort of back pocket. Let me like go back to it. It was something like less than 2 pow or something. Nat LT 2 pow self. Yeah. So we have this like, we have this statement for natural numbers. And like this is the only like real statement that we have, but we can like work our way around it. So nat dot less LT2 pow self. So this gets us this inequality, right? Times, so really, yeah, so this is x minus 100 times 2 to the 100. And what we have to prove is that this is less than this other thing, right? And the point is that this is true. This is not true for all x, but it is true for sufficiently large x, right? Like, for example, we need x greater than like 100. Yeah, we definitely need x to be at least 100 so that it makes sense to take the floor of it. But if x is greater than 100, then, you know, this holds true because what we have on the side here is like 2 to the 100, like this. So yeah, so this is true for sufficiently large x, copy, paste. And the thing that I'm additionally going to do here is that this is greater than like x minus 101. And the point is that, like, okay, for sufficiently large x, this is also true. So I guess I should also write that this is true for sufficiently large x. Because if this is true for sufficiently large x, then we can like go all the way down the line. And this is true for sufficiently large x because we're talking about x times 2 to the 100. So this grows much faster. So it must be true. So all of that seems sensible. So this seems like a solid plan, right? And so this gets me like that the equality holds true for x greater than 100. And then how do I get like anything less than 100? Well, I can just go, in theory, I mean, I don't have to go all the way to 100. I can probably choose a number much less than 100 here. But I can just go like, okay, I have to prove it for all x greater than 4, right? So I can say, okay, on the range 4 to 5, this is going to be less than like 10. And this is going to be greater than 16. And then on the range 5 to 6, this will be greater than 32. And this will be less than like 12 or whatever. And so I can like proceed in that fashion. So I think that all will work. So I guess first order of business is to try and determine what is the value of like the lowest value of 100 for which all of this logic will work. Yes, what is the lowest value of 100 for which all of this logic will work? And the answer is probably like 5 or something. Yes, so let's like redo all this with 5. So all these 100s, let's make them 5. Yeah. So all of this is like the, so okay, like let's like try and point out here all the times where we need like a sufficiently large x. I think here, the problem is we're taking like the floor of a real number to a natural, and like that we're not doing the traditional floor. What we're actually doing is the floor that takes you to like, that for negative numbers goes to 0. It's like positive floor. I feel like there's a name for that or something, like floor plus or whatever. Floor, isn't it like real dot floor? I forget what it's called. Floor ring, yes, but the real floor is not exactly what we want. Okay, whatever. Yeah, so let me just try and think through, does this hold, right? X minus 6. So, I mean, first of all, this holds like true for x greater than 5, sure. Because if x is greater than 5, then this is getting rounded down. Sorry, I guess it's more proper to say that this is true for x greater than 5. This is just a simple equality. This, okay, and this goes to this. Let's just write this out. Holds by nat.lt to pow self. Right, we can even say that this is an equality, right? Now, immediately above this, okay, so we're talking about x minus 6 goes to x minus 5. Let me just think about this. X minus 6 is always going to be less than that. Yeah, I mean, it's definitely true for x greater than 5. I think it's just true for all x, but whatever. And then this step is true for sufficiently large x. So we're like back in the land of reals now. I'm gonna do some type descriptions so that I know what I'm doing. So this is a natural, this is a natural, this is a statement about naturals. And this is a statement about reals. And so we have this to this, right? For what x does this hold? The point is that this can be proven by like simple like linearith. And it's true for x sufficiently large. It's true for x greater than 5, at least. For x greater than 5. Sorry, no. What is true for x greater than 5 is like this one. So they're all true for x greater than 5. I should just proceed with the x greater than 5 plan. So let's try and do this. Okay, let's try and proceed. I mean, okay, so we have one fact, which I still don't know how I'm going to prove, which is that this is less than or equal to 2. Yeah, just a like totally a random fact about some number. I don't know if it's considered better to like inline it or outline it. Let's see if I can like construct the calc block. By calc. Okay, no, the first thing I want to do is do a by cases on whether x is greater than 5. By cases h 5 multi-x. Okay, and we can create casework for all this. So this is the case where it's greater than 5, and this is the case where it's less than 5. Cool. Sorry and sorry. And now let's proceed with this case, which I am thinking is going to be a calc block. So calc. So the first step of the calc block is to say that the first thing that we have is less than or equal to 2 times x, colon, by, sorry. Oh, I guess it's colon equals? Yeah, okay, that makes sense. Let me just like copy this proof plan up here. Okay, so that first. Now we have this is less than, yeah, less than or equal to that, by sorry, correct. Type mismatch, has type Z, yeah. So, but isn't there like a underscore plus? Yes, the greatest natural number n such that n is less than or equal to a. If a is negative, then it's 0. What is it called? R floor? No. But where is it defined? Go to definition. Nat.floor. Okay. So it's just called nat.floor. It's called nat.floor. It's a function called nat.floor for real numbers. And it has successfully been defined for any possible type that you could care to mention. Cool, that's fine. Let's continue with the autoformalization. 2 to the power, yes. That's that step. That's that step. That's that step. Calc expression has type. Yes, the classic calc expression has this type, but is expected to have this other type, which looks exactly the same. So RRR, LE, ooh, LT. Yes, the problem is, what is the problem? The problem is that I've proven that it's strictly less than, whereas I wanted to only prove it was less than or equal. That should be fixed by doing this and then doing the weaker thing. No goals to be solved. Cool. So all of that seems fine. Yes. Okay, so how is this proven? This is proven by proving this like brute fact about this number and that it's less than or equal to 2. Yeah, that seems fine. You can probably do that. Well, I don't know. Can we do that? I mean, we have to prove it's less than something at some point. Like hopefully, you know, hopefully it won't be too hard to like rework this whole thing if I need to like randomly change that bound or whatever. I don't know. Seems like there should be like a tactic for that kind of like fact, calculational inequality or whatever. Yeah. Okay. Cool. So let's like proceed with the proof. 2 times x is less than or equal to, yes. So this is by Linnerith. Failed to find a contradiction. Maybe it has to be norm than Linnerith? It's the problem that, okay, these are real numbers. Sorry, real number. Let me just like, yes, naturally we first do norm num, and that gives us that. Real number minus 6. What does it take to prove this? I really thought Linnerith was capable of proving things like this. I mean, the problem, like 5 is less than x. X is greater than 5. Why doesn't Linnerith find a contradiction here? Does it work better if it's like LE? I guess the problem is that we have these real numbers and it's not like smart enough to do like a division on them to figure out that this is it's not like smart enough to like divide 30, right? So what does it equate to? Is like 30, 0 is less than or equal to 30x minus some large value. Yeah, how big does x need to be? Maybe the problem is that what I had said was false. Does it work if I had like do 7x? Okay, yeah, obviously I'm just bad at math. So, right, the point is that instead of this, we are simply going to like find the largest number for which this holds and not worry about it too much. Yeah, the interesting question is like, okay, I could like play with the parameters here and like do, instead of subtraction by 4, right? But it doesn't matter because I'm already assuming x is less than 7, so I might as well do this. The question is, could I like go to 6 or whatever? 4 to 7. 7, 6 to 7, right? The point is that, okay, even if x is less than 7, then we have 14 on the 2x part, and that seems quite sufficient to like prove the bound on the so this will probably end up not being too verbose of a proof. Well, it'll be a pretty verbose proof, but it won't be as verbose as more verbose than it has to be in this approach. Okay, so what do I do here? Simp. Perhaps. And the remaining question is, how do I prove this? Right. So this is a natural. What am I being told to do here? No goals left to solve. I don't get why it says there's no goals left to solve. Did it prove the goal? I don't think it proved the goal because it doesn't have like an exact thing. So why does it say no goals left to solve? What if I put done here? Does it say, does done complain that I'm done? Okay, this is very strange. I feel like this is like something worth complaining about. Like, why does apply a question mark not cause this? Okay, simp. Like, let's squeeze our simps here. Set option linter.flexible false. This is what I was looking for the other day. I guess I don't need to do it now. Right, and so, okay, just to make sure that I'm comfortable with doing this as like a natural number, right? Okay, I'm trying to think through, yeah, how do I prove that this is less than that? So what I want to prove is that a nat floor of a real is no more than 1 less than that real. So, okay, let's try and look things up. Nat floor, what we're trying to prove is that nat floor is greater than sub 1. I'm also not typing it right. Nav floor sub 1. Nav floor sub 1 LE. Right. It's something along these lines. Sub 1 LT floor, this one. This is what I wanted, right? Yeah, so I'm trying to prove that this is like a sufficiently large thing. This is a nat cast. Sorry. I think what I want to do, okay, so these are reals still. So maybe I don't want to simplify. What I simply want to do is I want to introduce to the context nat dot have this, which is nat applied to the real number 5. No, not this. The real number x minus 5. And then Linnerith. No goals be solved. Yeah, okay, cool. So that was, yeah, I basically just need this fact, and then I'm good. Cool. What happens next is I go here. So this is where I apply nat.lt2 self, right? So this is a natural number. And so let's like again do the trick of like introducing to the context. Not nat. Okay, but again we want this applied to this natural number here. Function expected. Just a sec. Nat.lt2 self. Okay, apparently it doesn't, I don't know how to do this. Oh, that's one of the cases of like feel like overzealous implicitness. Okay, does Linnerith now work? Failed to find a contradiction. Okay, I mean like we're multiplying by this, so like can I simp away the multiplication by 2 to the power 5? Mul eq mul right if. Okay, I just want to split it with this. Get the indentation correct. Left. Okay, 2 the real okay, I understand. I understand. The problem is that we have 2 as a real number. The problem is that this expression still has 2 as a real number. Yes. So this is 2 as a real number. So what we would like to do is just add another 1. So this is where 2 is a real number. That should be fine. 2 will eventually have to be a real number, but it will start out as a natural number. If I can type correctly. First, 2 is a natural number. So now we ask ourselves, does this proof work? Failed to find a contradiction again. Okay. Yeah, we should pass, let me think. This is the real number, this is a real number, but that should be fine. Maybe the point is that we need this first, because we need to like get the like real part out. Okay. We have this, and now left. And now this should be, okay, cast real. It's a real number. I don't want it to be a real number. Just a moment. Why is this a real number? This is a natural number. It's the problem that we cannot leave. Okay, the issue is that like within the calc block, we can't like switch between comparing natural numbers and real numbers. So I can't like have one inequality in here, which is an inequality about natural numbers. Okay, so yeah, I need to rethink this. This needs to go away. This is the point. Point is, I'm trying to prove this. And I'm here. And the thing that I have is that this is a real number too. This is a natural number. This is a natural number. Okay, also this is not an equality. This is a inequality. That's just patently absurd. This has to be an LE. Okay. Can I simplify this away? I need to like cancel on the right. That's what I need to do. Mul cancel Ugh, what billions of names for this operation that I'm trying to do here. Okay, yeah, it's interesting that it's like a RNR power, but whatever. Okay, how do I find this? How do I find the name of this lemma? The point is that I need to go to like Lugal or something. Lugal. Right. It's sort of weird to me that you can do like something mol something is less than or equal to something mol something. Fine. It's still loading, right? Mol left. Well, this is for nats, but I need mol right is the version that I need. Okay, what is the structure of mol right? ENN real. No, I want like real dot mol right. Okay, but what's it called? Okay, I just have to give up and do this stupid example thing. Example, I have 3 real numbers, A, B, and C. They're all real numbers, and I want to prove that A times C is less than or equal to B times C. The facts that I have are HC, which is that 0 is less than or equal to C. In fact, it's strict. Isn't this just true? If and only if A, L, E, B. Okay, we're gonna find the name. Mol if of pause right. Oh, so many words, have to have so many words in my lemma statement, can't just automatically find it. Bilinarith. I need a bilinarith here. So that's cool. So that like simplifies that away. Wonderful. And now, okay, what do we have here? This is the real. We're back at the point where I have this real. Don't need this. Yeah, in fact, I want to like apply LE of LT. Just so that it's of the exact same form. So this is a, they're both LT lemmas, and then I want to like convert this or something. Ooh, not enough. The problem is that they're of different types, and I needed to realize that these are just 2 casts of each other here. Nat.cast. This is a real number, which is a natural number, which is derived from a real number. A natural number being cast back to a real number. Whereas this is simply a natural number. So this is like some like cast thing. Sorry, where am I here? Is there like an exact for this? Could not close the goal. Right. So the point is I have some natural numbers and I need to cast them to reals. It's always so hard to get it to like, I don't know like what to say to get it to work. Where am I? I want to like go back. Yes. Example. Come on. Copy. Paste. I want an example where I have A, B are natural numbers. And I want to show that if A is less than B, then A, the real number, is less than B, the real number. Cast LT Emperor. M and N are natural numbers. I guess the point is I can just rewrite this. Or can I? Maybe I can't because it doesn't really think of this as a natural number that's been cast to something. At this, I'm going to rewrite it backwards, and I'm going to say, I'm going to like tell it, I'm going to have to tell it the type. So in this case, alpha is the real numbers. So alpha equals real. At this. Cool. Exact still doesn't work, but now we have this. Can we like push cast at this? Let me see. This is nat.cast, right? This is a natural number. Push cast at this. Now I can exact this. Cool. Got him. Excellent. Okay, so now we're back in the land of real numbers. And this is a real number, so we can like continue with our proof here. This is not just like a very straightforward fact about exponents. How add. What is rpal add? Yes, rpal add. But why not just like move forward? This is a natural. This is a natural. I just want a pow add actually. What about just pow add? And I guess the point is that this can be the equality. No goals. Cool. Moving ever onward. So these are real numbers now, apparently. Who knows how that came to be. This is a real number. This is a real number. Okay, apply pal leval. The issue is that this is a real number. Yeah, I mean, the point that I want to invoke is that like x minus 5 is less than this other thing. Okay, there should be something like pow le. Should be a part of the name. Pow le, but it shouldn't be this. Can it be like real.pow? What are the types here again? They are nat. Nat. I mean, the thing is that the bases are what are equals, so it should be something like apply nat polypal of le right. Polypal of le right, but it doesn't. It needs to not be a nat real. Polypal of le right. Unknown constant. What if I just remove unknown identifier? Yet again, I have to make an example because like there's no like clear way of finding. Ugh. Okay, I have a simple. Let me just slow down. We had a real number. We have okay. I mean, if in fact it's just like 2, right? It's just the real number 2. The point is that I want to just subtract this away, subtract this away. That is less than that. I have this by sorry. Now can I get exact? I guess the point is that I also am going to need to prove that 2, the real number, is deterministic timeout. Okay, is it getting to the point where it like can't handle my proofs anymore? That's always annoying. Can I like refactor this? What am I trying to prove here again? I'm trying to prove that 2 less than x is greater than that for like sufficiently large x or something. Here, let me reformulate this as a lemma. I'm trying to prove this. We're going to above, where's the theorem? Yeah. Theorem. 2 mol LT2 pow. It's a theorem about reals. about a real number x. X is a real number. hx. 7 less than or equal to x. The theorem that I'm proving is that 2, the real number 2, that all seems correct. Sorry. Okay, and the point is that I'm going to go back down to this calc block again now. And I'm going to start copying and pasting all of this. Copy and paste this whole calc block. Okay, I don't need this because, yeah, okay, so we're back where we were, sort of. We're just trying to prove this statement. Exact. Exact and not close goal. And the other fact that I have is have to pause. Is this sufficient? 2 is a positive number. That is less than that. I really don't know like what else I can do to like, surely, I don't get it. I have this, I have that as a positive number. Oh, it has to be greater than 1 perhaps. Greater than or equal to 1. It's always, yeah, you always have to do all this like reverse mathematics to figure out what's going on. Really? There should be Pow. What is this? What is the lemma? What do I do here? Pow. See, there's all this like bullshit about this like monoid with 0. Like I just want the fact about real numbers, please. Okay. Yes. So much better to have like the general form where it's totally confusing and no one can use it for anything that they want to. A and B are real numbers. 2 is a real number. Everybody's a real number here. B is less than or equal to C. A is less than or equal to A to the power C. Is less than or equal to B to the power C. I exact something. Like apply. There should be like some apply lemma. Is this it? R-pow, Lee, R-pow. No. Is it? Wait, no. Did I write this correctly? No, sorry, I got it wrong. A to the B. A to the C. Apply. It just is not even possible of figuring it out. Maybe Google. Okay, maybe if I had like, we're looking for things where the base is the same. Base is not the same. Here the base is the same, but we have natural numbers. Base is not the same. Here base is the same, but we're dealing with natural numbers. Base is the same, but we're dealing with natural numbers. Natural numbers, natural numbers, natural numbers, natural numbers, natural numbers. Base is the same. And it's of type A, where A is a monoid with 0. A is a monoid with 0. Monoid with 0. I guess this is right. Powly, pow right 0. Maybe if I, so. Failed to unify. Okay, the problem is that my exponents are also, we are dealing with R-pow, right? Like this is a real number and this is a natural number. No, these are, okay, maybe the issue is that this is a real number. Okay, this is maybe what's being confusing. These are reals. So just a moment. This is a natural number. Maybe what needs to happen is that I have to do an additional one where I switch it to being a real number here. Copy, paste, where this is a real number. Yes, so, I mean, okay, so the thing I'm gonna do here is like congruence. I don't you doing this to me? 2 H pow R R R. This is H pow R N R. Is there like an exact lemma? Of course, this is now like perfectly working. Okay, we have a real number raised to the power of a natural. How, like, so there should be some lemma about pow and r pow. This is a natural number. Maybe if I do like the additional type ascriptions. Additional type ascription to natural. Now we have identified the rpow cast thing. Does exact work here? This is not boding well how long the exact is taking. This is a real number. So it worked when I did not have this cast in. In this case, I should be able to do conquer, right? Because push cast, unsolved goals. Okay, what the heck? This is a real number. This is a real number. We did conquer. We did push cast. Can we do conquer again? Okay. Maybe, can we do just this first? Whatever, interesting. By push cast and then conquer. Okay, cool. And here we now have this working. Yes, okay, cool. We've done all of our casting. This leaves this. This is a real number. This is a real number. Simp. I thought I had some lemma for this. It was like up here. I mean, the point is that it should be like floor LE, self. Is there such a lemma? Floor LE self. And floor LT. Not floor LE, yeah. No self, cool. I have floor LE. 5. Don't need a proof. Sorry, type class instance problem is stuck. So alpha, clearly alpha is the reals. Cast R, floor LE. Yeah. So if I simp only this, type mismatch. Why is there a type mismatch? Oh, the problem is I have to like violin or something. I need to have 0 is less than x minus 5 by Lenoreth. H05. Floor LE, sorry. Less than or equal. Function expected, term has type. Function expected, term has type. Oh, is it because I haven't finished? What? I just want the fact. Foo. I don't know what it's asking me. Function expected at nat floor LE H05. I don't even need this value is the point. And now it's happy. Now I can delete this. Cool, great. That removes that. Can delete this. By sorry. Hooray, okay. Yeah, so that proves this. Cool, that proves this lemma, which is that it's true for n less than 7. Or for 7, who knows. And the point is that if I try 6, it'll fail because one of the linearists will fail, yeah. But 7 is sufficient for our purposes. So if we turn down to like the geometric series estimate here, okay, Okay, so we have all of this, and instead of all of this, I'm just going to delete all of this, right? Because this is what we did. And this is exact. This is exact the dilemma that I had. Cool. So the things that remain are to prove. You have to like prove a few facts about certain numbers, certain like explicit calculator numbers being less than other numbers. This one should not be too hard, right? Let me just like a POW, real RPOW LE1 if and only if. It just is running out of heartbeats. RPOW LT1. Sorry. The point is that the point is that the base, the point is that the base is greater than 1 and the exponent is negative. The exponent should be negative and the base should be strictly greater than 1. So it should be applying this. I believe. North. And Linrith. Cool. Just like simply clear that, sorry. Very good. Okay, so proof plan, we can delete this proof plan thing now. And so the remaining SARs that we have, I don't think there's any like other SARs before this, are we have to prove that this is less than or equal to 2. And then we have to deal with the case. So we also have to deal with the case here of x being greater than 7. Now we already have that x is greater than or equal to 4. And now we can say x is less than or equal to 7. So actually, basically what I'm going to insert here is, what I'm going to insert here is like a quick note to say that this is less than or equal to 2 times x. I'm going to say this is sorry. I'm going to do all of this beforehand. I'm going to say apply LE trans. That seems about right. Sorry, this shouldn't be that. So now we have this sorry, and by cases can now be resolved by this exact. The whole calc block can be removed over here. Okay, so now we have two things. Now we have to prove that 2x is less than or equal to of this for this range. Right, so the point is that x is less than 7. Sorry, x is not greater than 7. Therefore, x is less than 7. Therefore, this is less than 14. On the other hand, x is greater than 4. Therefore, this is greater than 16. Contradiction. Calc. Underscore LE 14 by Linrith. LE 16. By Linrith. Sure. Now we have to just fix all these. Okay, I'm going to take a quick break. Okay. It's confused. Calc expression, have I not written the calc expression right? So here I'm trying to prove 2 times x. Prop, but it's expected to have type, yes. Natural, okay, probably the problem is that it needs to be like real numbers here. These are dealt with by Linrith, and then the remainder is 16 is less than this, follows from 4. I guess the next point is that this is 16 is in fact equal to 2 to the power 4. From num. We have, just to check, that's a real number, that's also a real number, and I feel like I just had a big fight with this. Apply this. Well, of course. What is this? X to the power Y. X to the power Z. The point is that it has to be real. I'm like constantly fighting the namespace here. Cool. And of course it's very happily reminding me that I need to do this. Cool. I think I can get rid of all this like proof plan stuff. Delete. Okay, so the only sorry remaining is this one. This is like mul less than whatever. Prime, that this is less than this. It's failed to, what is it? Failed to synthesize? Oh, it needs to be told that this is a real number perhaps. Maybe add linear or something. Because we already have the x is positive. Okay, so now we have like well and truly reduced to this situation. Can we do like norm num? What happens here? Norm num, field simp, perhaps. Right, field simp doesn't exactly work with field simp doesn't exactly work with inequalities. So that's not gonna work. What does simp want to do exactly? Mul inv rev. Yeah, I don't know how important that is. But I would like to, I mean, like, so first order of the business, let's get like the 4 on the other side so that it's right. Mul inv le. Norm num. Right. Inv lef. Does this have a le? Yeah. So it has been deprecated. Use this. And le com underscore 0. Right. Le sub. Fad le. Yeah, it's getting closer and closer. Yeah, we just have like a bunch of other random things to dispatch. That's fine. So all that we have to do is prove that 2 to the power of minus 1/4 is less than 7/8. Yeah, child's play. Yeah, how to go about doing that? As I knew, the exponent would be the problem here. Right. I wonder if there's like, okay, so if I take the log base 2 of both sides, then I get log base 2 of 7 minus log base 2 of 8 is greater than, or is less than negative 1/4. Log base 2 of 8 is like 3 or something. Okay, I'm gonna do, here's what I'm gonna do. Rewrite add com. Then I'm gonna rewrite this thing in reverse. I'm going to do norm num. Now I want to take the log base 2 of both sides. I take the log base 2 of both sides. Both of the resulting sides are negative. Right, I have log base 2 of 7 minus 3. Right, so basically the other way of looking at all of this is 8 is 2 to the 3rd power. I switched it over to this side, so I have 2 to the 3 plus 2 to the 3 minus 1/4 is less than or equal to 7. Yeah, like what is supposed to be the way of proving that? Is this like let me just like return to the Carleson to like the reference, because I'm pretty sure that like there's no explanation given for this, which is like, you know, reasonable, but yes, let's see. Yeah, it is like simply the case that this is less than this, and the like fact that it's less than 2 or whatever is its own theorem. Do they like have log 7, for example? Log 3. No. They have log 2, an approximation to log 2, but they don't have log 3. Yeah. I mean, it kills me to like actually prove this when I know like the right way for this to be proved is for someone to have written a tactic to prove it long ago and for it to be immediately applied here. So I'm a little skeptical of all of that. So I think what I might just try and do is like extract this as a lemma, and like prove the lemma later, just to like highlight that this is like a lemma about a particular number. Like really that could have been said like of this situation, right? These are just like logarithmico-exponential functions, and it should be like not impossible to just prove bounds on them. Okay, whatever. Yeah, so I think I'm just gonna do that. Lemma. I'll just like extract this other lemma here. Call it a lemma. 2. It is a fact of this form. Sorry. I just like want to like double check one more time that what I'm doing is actually a true statement, because it's like you never want to like learn that you were proving something false later. The inverse of 4 times quantity 1 minus 2 to the power quantity -1/4. Yeah, it's definitely less than 2. So I'm going to copy out the proof just so that the proof progress is saved. Just a lot of statements. Exact can now prove this. And the rest of the theorem is proven relative to this. Unsolved goals. Sorry. Okay, so why don't I go through the process of like trying to like begin the PR to like see, because maybe they don't like care, or maybe they have like a good other way of proving this. So how do I write this pull request? If I go back here on GitHub, let's see, contributing. How to contribute. Contributions are welcome. If you start formalizing any of the results mentioned in the proof, please announce this on the Zulip first in the Carleson channel. Yes, I did that. Small fixes are always welcome and need not be discussed in advance. Simply make a pull request with a change. Note, the HTML blueprint has some rendering issues with certain equations and references. Consult the PDF if you see this on the HTML page. Some remarks. Some statements will be missing hypotheses. Don't hesitate adding hypotheses to a result, especially if it's already assumed elsewhere. Yes. I mean, I guess this is sort of analogous to the like, ooh, the n here was being interpreted as a real, but it has to be a natural. Add small additional lemmas liberally. Okay, cool. Yeah, I did that. Good. Some statements might need to be modified or additional lemmas added. Some estimates about I could actually even be more liberal technically, but some statements might need to be modified or additional lemmas added. Yeah, I did that. Feel free to change definitions, theorem statements to more convenient versions. Yeah. Basically, you know, this is just like a chill proving environment. Very good. Suprema is probably most convenient to take Suprema over this, and potentially apply n real to real afterwards. Most inequalities are up to some constant factor. Put these constants in separate definition. Feel free to improve these constants. If you're writing lemmas yourself, take a look at the class proof data, which contains a lot of the common data assumptions used without sections 2 to 8. Just a bunch of math frac characters. Cool. I don't think this is like relevant to me. Okay, so I just need to make a pull request. So let's try and do that. So we've added some things. We added this basic file and this. Let's switch our branch to a new branch called Bailey lemma. I think it was 10.1.1. Sorry. 10.1.1. 10.1.1. Enter. Okay, cool. Make a lemma or make a branch. Just gonna reopen these. Good to always have them open and add my changes. Commit. Proved relative to calculator fact. I'm just gonna commit this. I will publish the branch. It will tell me that I need to create a fork and push to that instead. Yes, I create my fork. Create GitHub fork, pushing changes. Successfully created on GitHub. Let us open it on GitHub. Okay, cool. In fact, I can probably just do this here. So yeah, compare and pull request. Feet. Okay, well, let's take a look at what the pull request conventions are. I guess I would call this a WIP. WIP. Lemma 10.1.1. Currently proved to fact about relative to create pull request. So the question is I mean, the sense that I get is that they do not necessarily care too much about getting it golfed to all get out like they would in MATLAB. Okay, we just have a bunch of examples here that we can get rid of. Save. Is there anything in here? Yeah, I think that's fun. So I'm going to, just close this other thing. Delete comments. Commit. Sync changes. And what exactly happens to the pull request when I do this? Okay, yeah, clearly we get another one. There's no conflicts with the base branch, and I can inspect. Here, let me. Right, so that's still in progress. We have this additional fact, that's this sort of obvious fact that needs to go into MATLAB. Cool. Yeah, we just need to do all of this. And then we have this, so this is the original formulation, except for one small change, which is nat. Some should be over nat, which is, I'm almost certain, I would have to be really not understanding things if that's not a correct change. Okay, cool. Great, that seems pretty good. And maybe enough work for today until I can figure out how to prove calculator-based facts. Yeah, seems good. So I'm gonna sign off.